And welcome back. Welcome to the second unit of this course. We have now finished with the unit circle. Not necessarily forgetting what we've done, but rather taking that and bringing it into a new context. We start looking at triangles. In this unit, we will start with right triangles, everyone's favorite familiar topic from trigonometry, SOHCAHTOA and the like. And then from there, we will go into general triangles, things that don't necessarily have right angles to them. And then from there, we will get into what we call analytic trigonometry, where we dispense with geometric shapes altogether. No circles, no triangles, just pure math, pure trigonometry. And that's where we're going to stop this unit in. So let's get right to it. Starting off with right triangles, and that is a triangle where one of the interior angles is 90 degrees. So the way I want us to kick off this unit is to start almost exactly where we left off. See, we had here some triangle of some radius. I'm sorry, some circle of some radius. Wow, that's embarrassing. Right, we have some circle of some radius. Radius not necessarily 1, although if it were equal to 1, we would be on the unit circle, because we would be the unit circle. But more generally, let's say my radius is 2, maybe 1.5, 1.7, whatever I can get this thing to stop at, 1.74. So that's the radius of my circle. And I am doing generalized rotation about it. Now, what we had stopped with in the last unit was, okay, I could inscribe a triangle into my circle based on my point. I would have my hypotenuse go from the origin to my terminal point. I would then drop a vertical down to the x-axis, or alternatively up to the x-axis, depending on where my point was. And that would produce a right triangle. Right, we see here that this is a right angle, and we are able to relate this terminal point to the dimensions of this right triangle. We were able to do so because we had a similar right triangle, a similar triangle being formed on the unit circle, right? R equal 1 produces that unit circle. And so we have some triangle which we understand what this is, right? This is of radius 1. This terminal point is cosine t comma sine t, where t is the amount we moved around, but also equivalently the angle of rotation. So the angle of rotation that put us here, maybe call that theta or t, that put us at a point we recognize. But that was for a circle of radius 1. To go from a circle of radius 1 to a circle of radius r, well, I have to multiply 1 by r to get out to here. But in doing so, similar triangles means, well, to go from 1 to here, right, to go from here to here, I have to multiply this distance by r. So this went from cosine t to r cosine t. This height, which is now r times sine t, is, well, exactly that, r sine t. So we were able to end last unit recognizing that for a general circle of general radius r with general angle of rotation theta, our terminal point is now r cosine theta, r sine theta. So setting x equal to r cosine theta, we can say definitively for any circle of any radius, cosine theta is x over r. Similarly, for y being r sine theta now, not just sine theta, but r sine theta, we can say that sine theta is the ratio of y to r, where y is the y-coordinate of the point I'm at, and r is the radius of the circle I'm moving on. And then tangent, accordingly, is the ratio of sine to cosine, which reduces down to be y over x. And then we have the reciprocal functions as before. Now, before we move on, I want you to recognize that this is not different necessarily from how we defined sine, cosine, and tangent in the previous unit on the unit circle. Right? The cosine of theta was not x over r there, it was just x. But that was because on the unit circle, r was equal to 1. So this equation, cosine theta being x over r, still holds on the unit circle. It's just r is 1. By the same token, sine of theta being y over r means that sine of theta is equal to y if you're on the unit circle. So this is the same thing we've had before, just now more general. But what I want us to do in this unit, the way I want us to start this unit off, is instead of worrying about the circle, let's not even look at the circle at all. Let's look just at the corresponding triangle that is produced as we move around. Each time, each place we end up at for any angle of rotation, we have the hypotenuse, which is r for the circle, but just in general, the hypotenuse, the longest side of a triangle, longest side of a right triangle. We have some interior angle theta here, which is not necessarily the angle of rotation, but rather just the reference angle to it. But we have some interior angle here. And then also we have the side adjacent to that angle and the side opposite to that angle. Note that I also have an angle up here, call it something else, maybe phi or alpha, whatever angle this is. If that was the angle in which you were interested in, then this side, where it is the adjacent now, would become the opposite to this angle. And this side, which is opposite to theta, would then be adjacent to whatever this angle is. So it's all relative, but at the same time, for theta, it's fixed, right? For theta, I have an opposite side, I have an adjacent side, and I have a hypotenuse side. And so, for the right triangle with that acute angle theta, we can rewrite our trigonometric expressions not using symbols, but rather using words. Right? The ratio of opposite to hypotenuse is sine. Right? Because on my triangle, hypotenuse was my radius, and the side opposite that was my y. So y over r, opposite over hypotenuse, sine theta for any triangle is opposite over hypotenuse. Also, furthermore, adjacent over hypotenuse is cosine, and opposite over adjacent is tangent. All of those follow by looking at this being inscribed on the unit circle. Or not just on the unit circle, but on any circle now. So these are what we're going to look at for the start of this unit. So I have a question for you. Because, yeah, we've reached the end of our first video. There will be one more to follow, and then we'll be done for now. I've got a triangle. Triangle usually listed as triangle ABC. And the dimensions of it are shown here. Watermark, because I did just take this picture from Analyze Map. It's got vertices A, B, and C. C is a right angle. So based on that information, and based on the fact that the side opposite B is 3, and the side adjacent to B is 4, what is sine of B? One thing you're going to have to do before you say this, I imagine, is check for the length of the unknown side. Right? Because we do have a right triangle, not only do we have these three ratios at our disposal, we also have two other bits of information. One being that the sum of all the interior angles add up to 180 degrees, or pi radians if you're using radian measure, and that's because that's just what it means to be a triangle. But what it means to be a right triangle is you also get access to the Pythagorean theorem, which is a squared plus b squared equals c squared, where c is the longest side. Only true for right triangles, but again, this is a right triangle. So, using this information, what is sine of b? And that's how we end up. So we will pick up from there in the next video. I will see you then.